One principle in general chemistry, Le Chatelier's principle, sometimes pronounced Le Chatelier's principle, depending on your dialect. This is just a principle that we see when it comes to reactions that have an equilibrium about them. And dynamic equilibrium, that's just as a little bit of reactant gets converted into product, at the same time a little bit of product gets converted back to reactant. Therefore, even though the chemical reaction is still going back and forth, the concentrations of everything, reactants and products, are still staying the same. So what happens though if we are currently in a dynamic equilibrium and some stressor is added to the system? The equilibrium will shift in such a way, or the stress shifts the equilibrium in such a way that the chemical reaction will need to move either forwards or backwards until equilibrium is reestablished. And some examples that we'll see in general chemistry lab include altering the concentrations either of the reactant or product, changing the temperature of a chemical reaction is currently undergoing, or changing the pressure as well. One excellent example to model all of these possible principles is what if we had a equilibrium reaction where on the reactant side we have molecular nitrogen gas and molecular hydrogen gas in equilibrium with ammonia gas on the product side. And for this particular example, we're going to have heat as a product or heat as if it is a exothermic reaction. The stresses that we're going to look at are what if we increase the concentration of, say, one of our reactants, molecular nitrogen, or if we decrease one of our reactant concentrations, molecular hydrogen. What if we increase the temperature or decrease the temperature that our reaction is currently undergoing, or what if we modify the pressure as well? Here's what happens if we do all of that. Now, no matter what kind of equilibrium we have, we will always affect it if we change the concentration of any of our chemical species. For example, for a reactant, if our reaction is at equilibrium and we arbitrarily add more molecular nitrogen gas. Well, in order to reestablish equilibrium, that stress is going to cause our reaction to move in the forward direction to use up some of that excess nitrogen and form some more ammonia gas. Until equilibrium is reestablished, then the concentrations will reach some equilibrium amount that's no longer changing in value. If instead, though, we were to decrease the concentration of one of our reactants, like hydrogen, well, we have lowered it, therefore we have, say, an excess of product compared to reactants. This stress will encourage the chemical reaction to move in the backwards direction and decrease the concentration of ammonia and increase the concentration of nitrogen and hydrogen until that equilibrium is reestablished. And then those concentrations will no longer be changing, even though the reaction is still moving backwards and forwards. That's to help offset the reduced reactant amount. Now, the same thing applies if we were to, say, add excess products, then that would move the reaction in the backwards direction. If we were to take away products, then that would move the reaction in the forward direction until we have some reestablished equilibrium. If we affect temperature, these only affect chemical reactions where heat is either a reactant or a product. In other words, we need our delta enthalpy of reaction, delta H, to not equal 0. If that's the case, then changing temperature will affect our chemical reaction. In this particular example, we're working with an exothermic reaction. Heat is thought of as a product. So if we were to take this chemical reaction at equilibrium and increase the temperature of that chemical reaction, that's almost as if we're adding excess products to this exothermic reaction. Therefore, the equilibrium will shift in the reverse or in the backwards direction so as to use up some of that excess heat as well as some ammonia to produce more nitrogen and hydrogen gases. This goes into the fact that equilibrium constants, they are thermodynamic constants. They do vary in value with temperature. Therefore, that affects the ratio of products to reactants. Now, for an exothermic reaction like this, if we were to decrease the temperature of the system, then the chemical reaction would want to reestablish that loss in heat and would move in the forward direction in order to replace that lost heat. If we were talking about an endothermic reaction where heat was a reactant, then the reverse is true. Whatever side heat is on our chemical reaction, just think of increasing or decreasing temperature as if we're increasing or decreasing the concentration of one of our reactants or products. And again, affecting temperature only affects the equilibrium of a chemical reaction if it depends on enthalpy, if enthalpy of that reaction is greater than or less than 0. Now, if we were to affect the pressure, change the pressure, this only has an effect if our reaction has at least one chemical species that has a gas. And specifically, where the moles of gas are not equal on both sides of a chemical equation. For example, for this particular chemical reaction, if we look at the stoichiometry, we have on our reactant side 1 mole of nitrogen gas and 3 moles of hydrogen gas that react together for a total number of 4 moles of gas. On our product side, we have 2 moles of ammonia gas. So 4 moles of gas on the reactant side, 2 on the product side. If we increase the pressure of our chemical reaction, this moves our reaction in the direction of lower number of moles of gas. Because we have less moles of gas on the product side, increasing this reaction's pressure pushes it in the forward direction. If we were to decrease the pressure of our system, then our chemical reaction can accommodate by having more moles of gas and therefore shifts in the direction to produce more moles of gas. If we had a chemical reaction where there's an equal number of moles of gas on both sides of our chemical reaction, hypothetically, if we had a chemical reaction that had, say, 1 mole of gas on the left side and 1 mole of gas on the right side, then affecting pressure will not actually affect the equilibrium whatsoever. Additionally, if we have a reaction where there are no gas species, if everything is just a liquid or just a solid, for the most part, those phases of matter are incompressible with pressure. Therefore, they won't be affected with pressure. So to combine all these things together, here are the special cases. If enthalpy of a reaction equals 0, then the equilibrium of that chemical reaction is temperature independent. Increasing or decreasing the temperature might speed up the rate of the chemical reaction. It will speed up the kinetics, but it will not affect the thermodynamic constants or the equilibrium expression. If there are no species in the gas state, the equilibrium is pressure independence. And I should also add that if there are an equal number of moles of gas on both sides of the chemical reaction, then that equilibrium is also pressure independence. So just added that in there. Again, if the chemical reaction has, say, just one chemical species on both sides of the chemical reaction, or whatever it is where the stoichiometry for the number of gas on the reactant side equals the total sum of the stoichiometry on the moles of gas on the product side. That will also be pressure independent. And lastly, we could add a catalyst. All that does is it increases the rate of the chemical reaction in both directions. Catalysts will affect both the forward direction and the reverse direction of a chemical reaction. Therefore, a catalyst will help get to equilibrium quicker, but it will not change the values of the concentrations of everything necessary to reach equilibrium. So, in any case, those are all the different factors that can affect an equilibrium if we're looking at Le Chatelier's principle. As always, likes and subscribes are never necessary, but they are fun to see, and I hope it helps grow the channel if you do. In any case, peace.